Okay, so to get things going a little bit, like we did last week, so our virtual lab session, in the lab notes in our Canvas page, down the lab notes, there are two files for this week. Um, the first one is a blank version of the problems. These are the problems that um, I want you guys to give a shot. I'll break you up into some smaller rooms. Um, but these problems also have their solutions. But like uh, we've done in the lab, trying the problems out on your own is far more beneficial than just looking up the answers and seeing, oh yeah, I get what they're saying here. So to try to build those mental connections is where most of the benefit comes. After you guys try these problems out for a while, we can come together and talk about them. um, but also, if uh, I'm not in the room, I will be sort of bouncing around between the rooms to help out. If you think you have an answer, you want to check it, or you're just super stuck and you don't want to wait for me, um, you can take a look at the solutions. So pull these up. I'm going to split you guys into a few rooms, and then we'll get going in 25-ish minutes. We'll come together and talk about them, and then there will be a quiz at the end that get in you'll get assigned to you, and there will be a place for you to upload it. So go check out those files on the Canvas page, and let me make some rooms for you guys. So people sorry, trying to split things up into the um, basically groups that they seem to be in before. Okay, cool, let's do that. Okay, so the other guys will come in here. Um, an option for going over these problems is, as you guys work through the first few, I was thinking that I could start at the bottom and work up, just so we make sure that we're not rushing through the problems that you guys didn't get to. Does that sound like a good plan?
Yeah, that's good.
All right, cool. So whenever the other group actually gets in here, we'll um, do that. Oh wait, are they here? Okay, sorry, just the first batch was all I could see. So let's do it. Solutions. Okay. So I guess a few things before we start going over the problems. In the prompt here, it says, if it converges, find the sum if possible. The way to really read this is there are very few cases where we know what the sum of the series is. Later, we will get another one, but for at least for this first part of the sequences and series stuff, we can find the sum if a series is geometric or if it's telescoping. If it's not one of those, then given a series, it's really hard to figure out what the sum is. And so in this kind of problem, how to interpret this line is really to say, if it's telescoping or geometric, I'll find the sum if it converges. If not, I just don't have to worry about it because that's not something that we really have the techniques to do. And then also concerning this test for divergence, you don't always have to do the test for divergence. If you look at a series and think, oh, I know this is geometric, and so I'll just use that. Or I know this is a P series, I'll just use that kind of test. So if you know what to do, you don't have to try the test for divergence. But if you're not sure what to do, it's a place to at least start. And it rules out kind of a lot of series. You just say, this is a pretty easy thing to check, and I can really quickly determine that they diverge. So you don't always have to start with that, but if you aren't sure how to proceed, it's a good first step. If the test for divergence doesn't apply, meaning the terms do go to zero, then you need to start thinking about what are the tests that I have and what do I look for in a series that suggests which test I should try to apply to it. So a lot like the integrals that we were doing at the beginning of the semester, we have all these things in our toolbox, and you have to, besides just figuring out how to use the tools, also learn to decide what is the best tool to use in a given situation. Okay. So starting from the bottom and working up to the problems that you guys went through already. So in this case, none of the tests that we really have seem to, or there's nothing that just really is being called out for. And so a good place to start with, if you're not sure what to do, is the test for divergence. And in this case, what we want to do is take the limit of the sequence here, but then if we're looking at this sequence, what we know is that because of this alternating part, the way that we really deal with that is take the limit of the non-alternating part. And in these alternating sequences, the breakdown is really, if you take the limit of the non-alternating part and get zero, then the alternating sequence goes to zero. If you take the limit of this non-alternating part and get anything other than zero, a number or doesn't exist or infinity, then the alternating part, the sequence with the alternating part doesn't exist. So in our case, if we're trying to use the test for divergence, the first thing is take the limit of the blue circled part. And in this case, the powers match. So look at the 3 and the 1 in front of those n squareds, and we get 3. What we can say is that since this sequence goes to 3, if we put on this -1 to the n, that makes it alternate, bounce between negative and positive, this limit isn't going to exist because part of it's going up to 3 and part of it's going to -3, depending on whether you get a positive or negative from this -1 to the end. And then that tells us what happens. The limit of the sequence, so the whole thing in red here, doesn't exist. And if the sequence doesn't have a limit, then the series is also going to diverge. Questions about that one? Okay, so this one is just the test drive for divergence, but within that, we still need to know what do we have to do to take the limit of this sequence, so we have to remember, in particular, how to deal with an alternating sequence like this. So next up is this series and this, oh shoot, there was a typo in this that was pointed out last time, we didn't fix it. So this is a geometric series. If we want to use the test for divergence, that means take the limit of this sequence. And if we're taking the limit of a geometric sequence, so not the sum part, but just the things we're adding up, the big focus is what is the thing you're raising to the nth power? And the breakdown is if this has absolute value less than 1, you're going to converge to 0. If this has absolute value greater than 1, then you're going to diverge. But in this case, we'll look at this r in here. It has absolute value less than 1, so this limit is 0. And that means test for divergence doesn't apply. We have to try something else. But this is a geometric series, and in deciding what the series does, we make the same observation. We look at the r in here, -2/9, and that is less than 1. And there's the same kind of thing that we check. R has absolute value less than 1, so we know it converges. But here, there's a typo in what the sum actually is. So why this isn't the right sum is that we actually are starting at n equals 1. So if we start at n equals 0, this is correct. A being the constant in here over 1 minus r. R is negative, so it's addition. So this is correct for starting with n equals 0. For n equals 1, what we have to do is that the bottom stays the same, but the top is the first term. So if we put in n equals 1, then we do actually get a factor of -2/9 here. So this is 6 times -2/9, and this is divided by 1 plus 2/9. So the bottom is always 1 minus r, but what's on the top, what matters is where are you starting. And for 0, it's just a. For 1, it's an a and the r. And it's in general, it's take this 1 and put it in the exponent. Whatever that first term you're adding up, that's what goes on top here. So this is a different fraction. We have to deal with that mess. But this does converge, and because it's geometric, we can find the sum. questions about this? In particular, the typo makes things confusing. Let me leave myself a note.
Is the 6 on top of that fraction or in front of the whole thing?
This 6 would be in the top of the fraction. So it would be like, let me try to, what it should be would be like there's negative, there's an extra -2/9 in the top of this fraction here.
Okay.
Is what it's supposed to look like.
Thanks.
Okay. So continuing to move up, the next one, 3/2n + 6. First thing, test for divergence. The bottom goes to infinity and the top is fixed, so this limit is 0. So the test for divergence doesn't apply. And if we start thinking about the other test that we have, well, it's not geometric. It is not a telescoping thing. And at this point, or kind of the, yeah. Yesterday, we introduced a new test which could apply, but other than the newest material, the only thing we can apply is the integral test. So the integral test means take this sequence we're adding up, rewrite it as a function instead, and then check 3 things. It's positive. That's true because if you're putting in positive numbers, everything's positive, so it stays positive. It's continuous because there's an asymptote at -3, but we're only looking at it from 1 to infinity. And it's decreasing because if you look at the bottom of the fraction, this is a line with a positive slope, so that is going up. And if you take something going up and you take its reciprocal, that is going down. So this function has these 3 properties. And usually, this is about as much as you would need to say. Sometimes, and we did one of these in class, if this is a more complicated function, you might have to take the derivative of it to see that the derivative is negative. But in a lot of cases, this is just kind of pointing out that it has to have these 3 properties, but it's not that hard to check that it has these properties. But after checking that this function is the type of function which our integral test applies to, what we have to do is take the limit, or we have to take the improper integral. So we have to remember how to do this. First up, that's a limit. Integrating, we have something in the bottom that gives us a natural log. This 3 stays there. Because we have a 2 and we're integrating, we divide by that constant, which gives us this 2 in the denominator. Then evaluate it from 1 to t. The t just changes the variable. If we put a 1 in, we get a natural log of 8. And now we take the limit, and the natural log goes to infinity. The fixed part stays fixed, so this limit is infinite. So we still have to remember how to do these improper integrals. But what we can say now, and what the integral test says, is that you did this integral and it diverges. The integral test says the series does the same thing. Because the integral diverges, the series diverges too. And if we got a number here, so the integral converged, the series would also converge, but probably to a different number. But we would know that it does have a sum. Questions about this problem? So to go out of order just a little bit, especially because C is about B here. In B, if you take the test for divergence, we see that that's the test that works. The limit of arctangent, it has a horizontal asymptote at pi over 2, because it's this kind of sideways tangent shape. And it has a horizontal asymptote of pi over 2. That's not 0, so it diverges by the test for divergence, and then we're done. So this is another kind of nice thing about the test for divergence. If it works, then you're quickly done and can move on to other questions. But what we also want to talk about, so we've done this, but if we change it a little bit, having 2 copies of this arctangent, the test for divergence doesn't apply. So we are taking the limit, we can take the limit of each piece separately, and they both go to pi over 2, so the limit of this sequence is 0. So we can't use the test for divergence here. But what we notice is it's the same function, arctangent, and they're being subtracted, but the insides are offset by just 1. And if that's the setup, the same function being subtracted, but 1 is shifted a little bit, that says it's going to be telescoping. So how telescoping works is that you start writing out the partial sums, meaning put in n equals 1, that gives us this, then add up the n equals 1 term and the n equals 2 term, and then we get some cancellation with the arctangent of 2 and negative arctangent of 2. Then we add up the n equals 1 and the n equals 2 and n equals 3 terms, and we get the cancellation we did before with the 2's, but then also with the 3's. And so we get negative arctangent of 1 plus arctan of 2. And then usually by 3, maybe 4, or you could go kind of as far as you want, but I'd say at least 3. We see that the pattern is this negative arctan of 1, that is never going to cancel. But what keeps happening is we get a different other term, arctan of 2 for the first case, arctan of 3 in the second sum, arctan of 4 in the third sum. So in general, if we add up stopping at n, we have arctangent of the next number on the inside. Whoa. And then what we do with this is that really how a series is defined, what this sum means is take a limit, take those partial sums and take a limit of those. And if that limit gives you a number, that is the sum that we're talking about. If this limit doesn't exist, then we say the series diverges. And now that we have an explicit formula, we can take the limit of this sequence. So the arctangent of 1 stays like it is. Arctangent of 1 is pi over 4. Taking the limit of this, we get pi over 2, as we've seen a couple of cases of, so that's pi over 2. And then adding these multiples of pi, we get pi over 4. So this series converges, and because it's telescoping, we can tell that it converges to pi over 4. Questions about this problem? Okay. So then the very last one, or the first one here, is 4 over n to the 6th. The limit 0 because the bottom goes to infinity and the top is fixed. One thing that doesn't matter is there's an extra 4 here. That's not going to affect converging or diverging. So we can really just say, you could factor that 4 out and think it's 1 over n to the 6th. And if that's the way you're looking at it, this is what we call the p series, meaning it's 1 over n to the p. And for this type of series, there is a clear dividing line. If this p is bigger than 1, the series converges. If the p is less than or equal to 1, it's going to diverge. Right, so in this case, it's a p series with p is 6. Since that's bigger than 1, the series converges by the p test, if you want to be extra explicit. And this one converges, but it's not one we can find the sum of, so we don't do anything with that. Okay. So I can stick around for a little bit answering some questions that you guys might have. In the next few minutes, watch for a quiz to get assigned to you. That's some more series that look like this using the test we've been talking about. And they say, here's a series, does it converge or diverge? There's some instructions there, but make sure you specify which type you're using and give all the justification that you need. So that the due time for it is, you'll have it like at least an hour, but make sure you do that. And then don't come to class tomorrow because we don't have class because it's a holiday. Okay, so I can stick around for a second. If you don't have any questions, watch for the quiz, and I'll see you guys next week.